In this video, we will cover the basics of transaction isolation, why isolation is needed, how snapshot isolation works with an example. Then we will look into the right-to-right conflict in Fabric Warehouse. Then finally, we end up with a real-world scenario where we faced this issue in our project, and we'll discuss the possible solution to prevent or resolve the problem caused by the snapshot isolation. Let us first start by understanding the need for an isolation level. Normally, when there are multiple transactions that runs at the same time, and there can be more than one transaction modifying the data while another is updating. Without proper control, this can lead to many problems like dirty read, inconsistent result, and lost update. So transaction isolation levels are used by databases to manage concurrency and ensure data consistency. So, snapshot isolation means each transaction works on a snapshot of the database as it existed at the time the transaction started. So each transaction sees a consistent data. To make this easier to understand, let's look at a real-world analogy of uh, of a bank account. Say you have a bank account and the bank balance at 10 a.m. is 10,000 rupees, and at 10:01 you open a mobile app to check for the balance and you see 10,000 rupees, and and at the 10:02 a.m. you try to withdraw. There is another person who has your ATM card and trying has withdrawn around 2,000 rupees from your bank balance. So that transaction is complete and committed, and your new balance now is 8,000 rupees. But the transaction A, which you initiated by using your mobile app, still try to see the bank balance as 10,000 rupees, because it is reading the snapshot that is taken at 10:01. 10:01. So this is snapshot isolation. Each transaction sees a consistent snapshot of the data as it existed at the time the transaction started, even if the data changes later due to other committed transaction. Now let's move on to snapshot isolation in Fabric Warehouse. One important thing to understand is that Fabric Warehouse, reads and write don't block each other. That means you can query a data while another transaction is modifying it, and vice versa. At first at first glance, this sounds similar to SQL Server, but here is where the behavior is very different. In SQL Server, multiple transactions can update the same table at the same time as long as they are not modifying the same row. However, in Fabric Warehouse, this level of concurrency is not allowed. Even if two transactions are trying to update different rows, Fabric does not permit multiple concurrent modification on the same table. Let me show you this with an example. I have two update statements, each targeting a different geography ID. The first update is wrapped inside a begin transaction, and I intentionally delay the commit using a wait for statement. So it would wait for about 30 seconds before committing. While this transaction is still running, I trigger the second update statement in parallel, updating a different geography ID. You will notice something interesting here. The second update statement succeeds without any issue. But when the first transaction finally tries to commit, it fails with an error saying snapshot isolation has failed due to an update conflict. This behavior is known as a right to right conflict in Fabric Warehouse. Write-to-write conflict occurs when two transactions attempt to modify the same table at the same time. This include operations like update, delete, merge, or even the truncate. And here is the key thing to remember. In Fabric Warehouse, even if two transactions are updating different rows within the same table, they can still conflict. This is because Fabric Warehouse uses table level locking under snapshot isolation. Now, what about insert operations? Do concurrent insert also cause snapshot isolation conflicts? The answer is no. And this is very important distinction to understand. The concurrent insert in Fabric do not cause snapshot isolation conflict. And here is why. Fabric Warehouse is built on delta tables and store data in one lake. The insert operation only adds new data files. So snapshot isolation conflict occurs only when the existing data files are changed or removed, not when new data is simply appended. Now let us understand a real scenario we actually faced in one of our projects. We used a metadata driven orchestration framework that executes both ingestion jobs and transformation jobs based on their defined dependencies. All the configurations as well as the runtime execution status of these jobs are stored in the Fabric warehouse. In the current implementation, job status is updated using a simple update statement. So the typical job life cycle looks like this. When a job starts, the status is set to running, and when the job finishes, the status is updated to either success or failed. But this is where the problem starts. A right to right conflict occur when multiple jobs complete at the same time and each of them try to update its status in the same table inside the warehouse. Let me actually simulate this issue for you. Assume that we have 8 parallel tasks all trying to update the execution status. As you can see in the we see these tasks are running in parallel and attempting to update the same table. And if you observe, you will notice that some of the task has failed. When we check the error message, we can see that the failure is due to snapshot isolation issue. This is the same error which we discussed earlier in this video. Now that we clearly understood the problem, let's talk about how we can redesign this pattern to avoid right-to-right conflicts altogether. So the first solution is to switch from an update-based approach to an append-only design. Instead of updating the job status using an update statement, we use insert statements to record each job status. In an append-only design, every job execution inserts a new record rather than modifying an existing one. This means multiple records can exist for a same job, each representing that a different execution or run. Now you might be wondering, if we have multiple records for same job, how do we know the current status? This is where query logic comes into the play. To determine the latest or current run status, we simply partition the data by job ID or an equivalent identifier, then order the execution using start time, end time, or even run ID, and then select the most recent record using some sort of a windowing function. Now let's move on to the second solution. This is the one we implemented in the project. Instead of changing the data model, we decided to retry the failed task. This approach was attractive for one simple reason: it requires no code change. The fabric pipelines comes with a built-in retry support where you can configure a retry count and a retry interval directly in the pipeline. But the problem is these retry settings are static. The retry count and the waiting interval are fixed. They can't be adjusted dynamically based on the type of error. And that leads to the second and the most important problem. For snapshot isolation errors, We want the task to keep retrying indefinitely until it finally succeeds. Unfortunately, that's not possible with a fixed retry approach. So this is where we moved on to a programmatic retry approach implemented using SQL and Python. Programmatic retry, on the other hand, provide much more greater flexibility. For a Python based programmatic retry approach, um, you can explicitly define the stop condition, like the maximum number of retry. You can have a wait strategy such as exponential backoff between the attempts. A typical retry logic looks like, first it catches the snapshot isolation conflict error, wait for a short interval, then it retry the operation and repeat this until the update succeeds. What you are seeing on the screen is a programmatic retry implementation in SQL. This code attempts to update a row in the ETL task execution log table, exactly the same update that was failing earlier due to snapshot isolation. The key difference is how we handle the failure. If Fabric throws a snapshot isolation conflict, especially error 3960, the code doesn't fail the job immediately. Instead, it catches the error, wait for 20 seconds, and then retry the update. This retry happens inside an infinite loop, meaning that the update keeps retrying until it finally succeeds. Since snapshot isolation conflicts are typically transient and caused by concurrent writes, retrying after a short wait almost always resolve the issue. Now let us look at the Python based implementation of the retry logic. For this, we have used a Python library called as Tenacity. The reason for using Tenacity is a decorator based API which makes retry logic very easy to plug into the existing code. In our implementation, we created a utility notebook, and inside that notebook, we defined the function that basically executes a SQL statement. And then we have a utility function um, that is decorated with the Tenacity retry decorator. Behind the scenes, this function basically Tenacity checks whether the raised exception is satisfied. You see the retry if exception function. If it does, then the Tenacity wait for 20 seconds and then re-execute the function. If it does not, then the exception is thrown normally and the task fails. The important thing to notice here is that we did not write any explicit loops. The retry logic is completely handled by the decorator itself. Now, to demonstrate how this works in practice, what we have done is we have created a utility function and placed it in one notebook, and then we created another notebook that runs the update statement. If you see that the parameters associated with this run state, the instance ID, the task ID, the status, and the message, then in order to parallelly trigger these 8 tasks, we are using run multiple function that basically trigger this notebook. If you click on one of the child notebook execution, you will notice that two different behavior. First task do not encounter any snapshot isolation. The update statement succeed immediately. There is no retry at all. But for the tasks that do hit a isolation conflict, you can clearly see the log message snapshot isolation conflict detected. And right after that, you will see the retry kicking and the Tenacity wait and then re-executing the function automatically. Next solution is to use an OLTP database. This is a Microsoft recommended approach because the Fabric warehouse, which is optimized for kill, read, and batch processing, it is not designed for a high frequency transactional update. So that is where the OLTP system comes into the picture, where it has a better row level locking, better concurrency handling,